In this video, I introduce generating open domain videos from natural distributions. GODIVA uses a vector quantization variational autoencoder to represent observable video X as a discrete latent code Z with lower dimensionality. The goal is to generate videos from a given text prompt T by modeling the conditional probability P. As shown here, this is the architecture of the model. This language embedding module, this encoder module, and this decoder module. The model uses three sparse tensions along row, column, and temporal directions to efficiently calculate the tension. For example, this along the row direction, this along the column direction, this along the temporal direction. I input video X with L frames with a resolution of H by W as shown here, and C channels to embedded as YL, where E is an embedding matrix, and the embedded latent variable Y is H by W ds dimensional tensor as shown here. YL is projected onto a codebook B by using this R minimum. ZI is encoded by the codebook B, and the code B is computed by using this equation, which are fed into a decoder to generate a reconstruction X caret as shown here. Finally, VQ variational autoencoder is trained by using the objective L as shown here, which includes three terms, namely reconstruction loss, codebook loss, and commitment loss. Where SG stands for stop gradient, SGX is equal to X in the forward path, and his derivative is equal to 0 in the backward path. The reconstruction loss measures the difference between the input frame X and the reconstructed frame X caret. The codebook loss measures the prediction SGY and the ground truth B. The commitment loss measures the difference between the encoder embeddings Y and the codebook SGB. Namely, the encoder embedding is similar to at least one code of the codebook as shown here, this input frame and this reconstruction. If the reconstruction same as the input frame, the reconstruction loss is 0. This latent space, this YL. If YL same as BL, the codebook loss is 0. If YL points at anyone in the codebook, the commitment loss is 0. To model the conditional probability P for video generation, an input text T is embedded as here, where ET is the embedding matrix, where S is vocabulary size, and D is embedding dimensionality, and PT is a positional embedding matrix. The pre-trained VQ variational autoencoder encodes each frame X in the ground truth video clip as shown here, where a sequence of tokens B are M ds dimensional tensor. The video embeddings are computed considering the positional information as shown here, using the text embeddings TE and video embeddings VE. The model decoder is trained to generate videos at each time step in an autoregressive way, as shown here. Three-dimensional sparse tensions, as shown here, as along row, column, and temporal, are applied to efficiently calculate three hidden states, HT, HR, and HC. That's right here. The sparse attention for each axis only attains to the tokens in the previous axis. The total attention HIGL is computed by stacking the three sparse attentions T, HT, HR, and HC. That's right here. A softmax function is applied to compute the probability of the predicted tokens using this formulation, where Z caret is the predicted visual tokens. Finally, the model is trained using the cross-entropy loss. That's right here. For more details, please check with these references. Thank you. Bye.